1.6 Technologies in Marine Engineering Sector. Marine engineering involves the design, construction, and maintenance of ships, boats, submarines, and offshore structures. It's a diverse field that incorporates various technologies to ensure the safe and efficient operation of marine vessels. Here are some key technologies in marine engineering. 1. Ship design and construction. Computer-aided design, CAD. Advanced software allows for the digital design and modeling of ships, enabling engineers to optimize hull shapes and improve efficiency. Finite element analysis, FEA software is used to simulate and analyze the structural integrity of ship components, ensuring they can withstand various loads and conditions. 3D printing, additive manufacturing techniques are applied to produce prototypes, customized components, and even entire ship parts, reducing manufacturing time and costs. 2. Propulsion systems. LNG and dual-fuel engines, adoption of engines that run on liquefied natural gas, LNG, or a combination of LNG and diesel for reduced emissions and improved efficiency. Pod propulsion, a propulsion system where the propeller is housed in a pod that can rotate, providing greater maneuverability and efficiency. Hybrid and electric propulsion, implementation of hybrid and fully electric propulsion systems to reduce reliance on traditional fuel sources and minimize environmental impact. 3. Automation and control systems. Integrated bridge systems, IBS, combining various navigation and communication systems into a single interface for streamlined ship operation and enhanced safety. Dynamic positioning systems, computer-controlled systems that automatically maintain a vessel's position and heading using thrusters and propellers, crucial for offshore operations. Condition monitoring, sensors and monitoring systems to assess the performance and health of engines, equipment, and structural components, enabling predictive maintenance. 4. Safety and navigation. Collision avoidance systems, radar, sonar, and AIS, automatic identification system, technologies are used to detect other vessels and obstacles, helping to avoid collisions. ECDIS, electronic chart display and information system, electronic navigation charts displayed on screens, replacing traditional paper charts for improved accuracy and efficiency. Voyage planning software, software solutions that assist in route planning, taking into account factors like weather conditions, fuel efficiency, and safety regulations. 5. Environmental technologies. Ballast water treatment, systems designed to treat ballast water, ensuring invasive species are not transported between different marine environments. Emission reduction technologies, exhaust gas cleaning systems, scrubbers, and selective catalytic reduction, SCR, systems are employed to reduce air pollutants from ships' emissions. Waste heat recovery, utilizing waste heat from engines to generate additional power or for other heating purposes, improving overall energy efficiency. 6. Offshore and subsea technologies. Offshore wind energy, innovative foundation designs and installation techniques for offshore wind farms, supporting the growth of renewable energy sources. Subsea robotics, remotely operated vehicles, ROVs, and autonomous underwater vehicles, AUVs, for underwater inspections, maintenance, and exploration in deep-sea environments. Floating LNG, FLNG, and FSRU, floating storage and regasification unit, floating facilities for liquefied natural gas, LNG, processing and storage, enabling gas production and regasification in offshore locations. 7. Material innovations. Corrosion-resistant materials, development of materials capable of withstanding harsh marine environments, reducing maintenance requirements. Advanced coatings, specialized coatings for ship hulls that improve hydrodynamics, reduce friction, and inhibit fouling, enhancing fuel efficiency and reducing environmental impact. 1.7 Mechanical properties of engineering materials. The mechanical properties of materials are key indicators of their behavior under applied forces or loads. These properties are crucial for engineers and materials scientists to understand when designing structures or selecting materials for specific applications. Here are some of the fundamental mechanical properties. Strength. Tensile strength, the maximum stress a material can withstand without breaking under tension. It is measured in units of force per unit area, e.g., megapascals. Yield strength, the stress at which a material begins to deform plastically, permanent deformation, and no longer returns to its original shape when the load is removed. Hardness. Resistance to deformation. Hardness measures a material's resistance to permanent deformation, scratching, or abrasion. Common hardness tests include Brinell, Rockwell, and Vickers hardness tests. Elasticity. Elastic modulus. Young's modulus describes the stiffness or rigidity of a material. It is the ratio of stress to strain within the elastic deformation range. Plasticity. Ductility, the ability of a material to undergo significant plastic deformation before rupture or fracture. Ductility is often measured by the percentage elongation or reduction in area during a tensile test. It is the ability of a material by which it can be drawn into thin wires. Malleability, the ability of a material to withstand deformation under compressive stress. It is often associated with the ability to form a thin sheet under rolling or hammering. It is the ability of the material by which it can be rolled into thin sheets. Toughness. Impact resistance, a measure of a material's ability to absorb energy during deformation or fracture. Toughness combines strength and ductility and is often assessed through impact tests like Charpy or ISOD tests. Stiffness. Flexural modulus, modulus of elasticity in flexure. Describes a material's resistance to bending. It is similar to Young's modulus but for bending loads. Fatigue resistance. Fatigue strength, the maximum stress a material can withstand for a specified number of cycles before failure occurs. This is important for materials subjected to repeated or cyclic loading. Creep resistance. Creep strength, the ability of a material to resist deformation under prolonged exposure to stress at elevated temperatures. Creep is particularly important in high-temperature applications. Corrosion resistance. Resistance to chemical attack. Metals can be susceptible to corrosion or degradation due to exposure to environmental factors. Corrosion resistance is crucial for materials used in harsh environments. Temperature resistance. High temperature strength. Some materials retain their strength and integrity at elevated temperatures, making them suitable for applications in high-temperature environments. These mechanical properties can vary significantly among different metals and alloys. The selection of a particular material for a specific application depends on the desired combination of these properties and the conditions to which the material will be exposed during its service life. 1.8 Classification of engineering materials. Engineering materials are broadly classified as A. Metals and B. Non-metals. In metals again we have two classes, i.e., ferrous and non-ferrous metals. The properties, suitability of different materials is discussed in the following session. Ferrous metals and alloys. Ferrous metals and alloys are materials that contain iron as their primary constituent. The term, ferrous, is derived from the Latin word, ferrum, which means iron. These materials are widely used in various industries due to their desirable properties, such as strength, durability, and magnetic characteristics. Here are some key categories and examples of ferrous metals and alloys. Iron. Pure iron is relatively soft and not commonly used in its pure form for structural applications. It is often alloyed with other elements to enhance its properties. Carbon steel. Carbon steel is an alloy of iron and carbon, with carbon being the primary alloying element. The carbon content in carbon steel typically ranges from 0.05% to 2.0%. The properties of carbon steel can be further modified by adding other alloying elements. Stainless steel. Stainless steel is an alloy of iron, chromium, nickel, and other elements. The addition of chromium provides corrosion resistance, while nickel enhances the material's strength and durability. Stainless steel is widely used in applications requiring resistance to corrosion and staining. Cast iron. Cast iron is a group of iron-carbon alloys with a carbon content greater than 2%. It is known for its excellent castability and is used in various applications, including pipes, engine blocks, and cookware. Alloy steels. Alloy steels are steels that contain elements other than carbon and iron. Common alloying elements include chromium, molybdenum, nickel, and manganese. These alloys are often used to enhance specific properties such as strength, hardness, and corrosion resistance. Tool steel. Tool steels are a specialized group of alloy steels designed for making tools. They typically contain tungsten, molybdenum, and vanadium, providing high hardness and wear resistance. Wrought iron. Wrought iron is a type of iron with a very low carbon content, making it strong, tough, and malleable. It was historically used for decorative purposes, but its use has declined in favor of other materials. Ferrous metals and alloys find applications in construction, automotive, aerospace, machinery, and many other industries. The choice of a particular ferrous material depends on the specific requirements of the application, such as strength, corrosion resistance, and cost. 1.8. A cast iron. Cast iron is a group of iron-carbon alloys with a carbon content greater than 2%. It has excellent castability, which means it can be easily melted and poured into molds to achieve complex shapes. Cast iron is known for its strength, wear resistance, and ability to withstand high temperatures. There are several types of cast iron, each with its unique properties and applications. The main types of cast iron include Gray cast iron. Composition: it contains carbon in the form of graphite flakes dispersed throughout the iron matrix. Properties: gray iron is known for its excellent castability, good machinability, and damping capacity. Applications: commonly used in engine blocks, pipes, and various machinery components. White cast iron. Composition: it has a high carbon content in the form of cementite, iron carbide, instead of graphite. Properties: white iron is extremely hard, brittle, and wear resistant, making it suitable for applications involving abrasion and erosion. Applications: used in applications such as wear resistant parts like grinding balls, liners, and crusher hammers. Ductile cast iron, nodular cast iron or spheroidal graphite iron. Composition: contains small amounts of magnesium or cerium, which cause the graphite to form in nodules or spheroids rather than flakes. Properties: ductile iron retains the castability of gray iron but with improved ductility, toughness, and tensile strength. Applications: commonly used in pipes, automotive components, crankshafts, and other applications where a combination of strength and ductility is required. Malleable iron. Composition: white iron is annealed, heat-treated, to convert some of the carbides into graphite nodules. Properties: malleable iron combines the castability of white iron with some ductility, making it more malleable and easier to machine. Applications: used in pipe fittings, agricultural equipment, and general machinery. Compacted graphite iron, CGI. Composition: a hybrid between gray and ductile iron, with a graphite structure that is intermediate between the flake-like structure of gray iron and the nodular structure of ductile iron. Properties: CGI offers a good balance of strength, ductility, and thermal conductivity. Applications: used in engine blocks, cylinder heads, and other components where high strength and good heat dissipation are required. Applications of cast iron: automotive industry, engine blocks, cylinder heads, brake discs, and exhaust manifolds. Construction, pipes, fittings, manhole covers, and architectural elements. Machinery, gearboxes, flywheels, pulleys, and various machine components. Cookware, traditional cast iron skillets, pans, and pots. Railways, brake shoes, railcar wheels, and other components. The specific type of cast iron chosen for a particular application depends on factors such as strength requirements, wear resistance, and machinability. 1.8.b Steels. Steel is an alloy of iron and carbon, and its properties can be further modified by adding various alloying elements. There are different grades of steel, each designed for specific applications based on their composition and properties. Here are some common grades of steel, along with their compositions and typical applications. Carbon steels. Composition: primarily composed of iron and carbon, with small amounts of other elements. Applications: used in a wide range of applications such as construction, structural steel, automotive, body panels, and machinery, shafts, gears. Alloy steels. Composition: alloyed with elements like chromium, nickel, molybdenum, and others to enhance specific properties. Applications: various applications based on the alloying elements. For example, chromium and molybdenum additions improve heat resistance and strength, making them suitable for high-temperature applications and tools. Stainless steel. Composition: iron, chromium, usually at least 10%, nickel, and other elements. Applications: known for their corrosion resistance, stainless steels are used in kitchen appliances, cutlery, chemical processing equipment, medical instruments, and architectural applications. Tool steels. Composition: alloyed with tungsten, molybdenum, cobalt, and vanadium. Applications: designed for tool manufacturing. High-speed tool steels are used for cutting tools, while cold work tool steels are used for making dies and molds. High-speed steel. Composition: contains high levels of tungsten, molybdenum, chromium, and vanadium. Applications: used for cutting tools at high speeds, such as drills and milling cutters. Carbon tool steels. Composition: higher carbon content than other carbon steels. Applications: suitable for tools that require a combination of hardness and toughness, such as chisels, hand saws, and woodworking tools. Weathering steels, CO. Composition: contains copper, chromium, and nickel. Applications: used in outdoor structures such as bridges, building facades, and sculptures due to their ability to develop a protective rust layer, reducing the need for painting. Spring steels. Composition: alloyed with elements like silicon and manganese. Applications: used for the manufacture of springs and high-strength, low-alloy structural components. Maraging steels. Composition: high levels of nickel and other alloying elements. Applications: known for their high strength and toughness, maraging steels are used in aerospace components and high-performance equipment. Abrasion-resistant steels. Composition: high carbon and manganese content, with alloying elements like chromium. Applications: used in mining, construction, and manufacturing applications where resistance to wear and abrasion is critical. It's important to note that within each category, there can be numerous specific grades with variations in composition to meet specific performance requirements for different applications. The choice of steel grade depends on factors such as desired mechanical properties, corrosion resistance, and the intended use of the material. 1.9 Effect of alloying elements on ferrous metals. Alloying elements play a crucial role in modifying the properties of ferrous metals, such as steel and cast iron. The addition of these elements can alter characteristics like strength, hardness, corrosion resistance, and more. Here are some common alloying elements in ferrous metals and their effects. Carbon, C. Effect: carbon is a primary alloying element in steel. It increases hardness, strength, and wear resistance. Higher carbon content typically results in harder but more brittle steel. Chromium, Cr. Effect: improves corrosion resistance, hardness, and wear resistance. Stainless steels, which contain chromium, are known for their resistance to rust and staining. Nickel, Ni. Effect: enhances toughness, ductility, and corrosion resistance. Nickel is often used in stainless steels and high-strength low-alloy (HSLA) steels. Manganese, Mn. Effect: increases strength, hardness, and wear resistance. Manganese is commonly used as a deoxidizer and desulfurizer in the production of steel. Molybdenum, Mo. Effect: improves strength, hardness, and high-temperature stability. Commonly used in high-strength low-alloy (HSLA) steels and tool steels. Vanadium, We. Effect: enhances strength, toughness, and wear resistance. Vanadium is often used in high-strength low-alloy (HSLA) steels and tool steels. Tungsten, W. Effect: increases hardness, wear resistance, and high-temperature stability. Tungsten is a common element in tool steels and high-speed steels. Copper, Co. Effect: improves corrosion resistance, especially in certain atmospheric conditions. Copper is often found in weathering steels, e.g., coartan. Silicon, Si. Effect: enhances strength, hardness, and magnetic properties. Silicon is commonly used as a deoxidizer in steel production. Titanium, T. Effect: improves strength and corrosion resistance. Titanium is often used as a grain refiner in certain steels. Cobalt, Co. Effect: improves high-temperature strength and wear resistance. Cobalt is commonly used in certain high-speed and tool steels. Nitrogen, N. Effect: enhances strength and hardness. Nitrogen is sometimes added to austenitic stainless steels to improve their strength. Sulfur, S. Effect: typically considered an impurity in steel. Excessive sulfur can reduce the material's ductility and toughness. Tin, Sn. Effect: tin is not commonly used as an alloying element in ferrous metals. However, when added in small amounts, it can improve the machinability of certain cast irons. Lead, Pb. Effect: lead is often used as a minor alloying element in certain free-machining steels. It enhances machinability but has a negative impact on some mechanical properties. Lead also acts as a lubricant during machining. Zinc, Zn. Effect: zinc is commonly used in galvanizing to provide corrosion resistance to ferrous metals. However, in terms of alloying, higher concentrations of zinc can cause embrittlement in certain steels, known as zinc embrittlement. This is a concern, especially in high-strength steels, as it can reduce toughness. Magnesium, Mg. Effect: magnesium is not typically used as an alloying element in ferrous metals due to its tendency to form intermetallic compounds that can adversely affect the material's properties. Magnesium is commonly used as an alloying element in aluminium-based alloys. The combination of these alloying elements allows metallurgists and engineers to tailor the properties of ferrous metals to meet specific requirements for different applications. The choice of alloying elements depends on factors such as the desired strength, hardness, corrosion resistance, and the intended use of the material.